Now the last operation that we can do on matrices, transposition. So we can compute the transpose of a matrix. It feels like a weird operation, but it's going to be linked to one of the most beautiful topic in Unit 4, which is like the least square methods, where we will merge everything together. Of course, right now probably you don't give a shit because, you know, you're just doing the shit home and you just want your marks. But if you truly care about like what's going on in this class, transposition will be at the core of one of the main computation of that least square method. Anyways, got too excited there. So the term transpose of a matrix, that is denoted a to the power t, so t for transpose. So you start with the n by n matrix. What you're going to get is you start with an m by n matrix, you're going to get an n by m, so the number of rows and columns are kind of swapped. And basically here, the entry of the transpose on the ith row jth column is the former entry AJI on the jth row and ith column, all that just to say that if you are computing the transpose, you just think about the first row of A and it becomes the first column of the transpose. The second row of A will become the second column, and then all the way down to the last row, the nth row of A will become the nth column of A. So let's just do some examples and you'll see right away what I mean by this. So first example here, we have the matrix A, and I'm just going to circle my rows. So the first row is 1, minus 3, 7. The second row is 2, minus 2, 4, and minus 2. And then the last row is 3. Let's use different colors here since we have nothing else to do. So second row in orange, and then the last row here, I'll do it in red. So 3, 5, 7, and 9. So the first row, the green row, becomes the first column of the transpose. So it just rise up. And then the second row, the 2 minus 2, 4 minus 2, becomes the second column. And then finally, the last red row, 3, 5, 7, and 9, becomes the last red column. So this is how you transpose. So always define. It's a very cute operation. And now let's just do this on one more example. So here we go. Let's compute A transpose first. Again, if I'm using old color scheme here, so my first row, so it's just a general square matrix. So in yellow, my second one will be in orange. My third one will be in red. And then let's end up with purple. Okay, so all these rows are going to rise up. So my A transpose, so my first column is going to be A11, A12, A13, A14. So that's my yellow column that comes from the yellow row. And here we go. So second column will be A21, A22, A23, A24. So that's my orange column. Yeah, this is fun. So my third column is A31, A32, A33, and A34. So that's my red column coming from my red row, third row. And then the last column, so A41, A42, A43, and A44. That's my purple. My purple row is now my purple column. Okay, and here we go. So that's A transpose. Beautiful. Next up, B transpose. So if we compute B transpose, so here, and actually you can, think about it as columns. You can start with columns, and then these columns they lay down. So for example, I could say like my first, let's say my first column would be 1, 1, 5 will become my first row. So you can do it row. You can do it. You can take the columns and just make them lay down. Okay, so it really doesn't matter how you do it as long as you do it correctly. So here, so B transpose, so the first row would be 1, 1, 5. And then, so that's for the yellow row. So first column becomes the first row. And then the 3, so if I use orange for the second one, the 3, 4, 6. So 3, 4, 6, and that's my orange row here. That's it for B transpose. Now if we compute C transpose, so here you can see C is a row matrix. Of course there's only one row here, 1, 3, 5, so that row will become a column. So here you just get 1, 3, 5, and that's your C transpose. And finally for D, well, that's very, very boring, of course, for D. I mean, you could argue that all of those examples were boring, but anyways, D in particular, very boring. So you get a 4, so when you transpose, nothing happens. So for D transpose, you're just getting 4 again. To some extent, you know, like you can, this is just a side note here, you can think about 1-by-1 matrices. Just a small remark here, I'll write that remark in red. So just a small remark with this matrix here. You could think about matrices, 1-by-1 matrices of real numbers, just as crazy notation for real numbers. And when you're talking about transposition, this is really an operation that is defined for matrices, because when you are doing transposition on real numbers, nothing is happening. So if you are, for example, trying to teach transposition when you only know numbers, it's kind of crazy. Like you could talk to like a kid who know about numbers and say, hey, do you know what's the transpose of 4? And the kid is like, no, it's 4 again. It's nice, No, it's... Anyways, so transposition for real numbers, it exists, but it does nothing, but it's really a true operation that emerges when you're looking at matrix structures. Anyways, that's it for that section. Let's talk about special matrices that we will have, that we will use a lot in the future. So zero matrices and identity matrices. So the first one, what is a zero matrix? So a zero matrix is just a box. So it's just a matrix filled with zeros. So if all the entries are 0, we're talking about a zero matrix. But of course, because there's different sizes of matrices, so there's different zero matrices, just like there's different zero vectors in our N. So in order to identify correctly which zero matrix we're talking to, we're going to use the notation. If you are talking about a matrix with m rows and n columns, then the corresponding zero matrix in that universe is going to be called 0 m by n. So if you want here, we have examples of zero matrices. So here we have a 2 by 2 matrix. So this is the zero matrix 0, 2, 2. Here we have a square 3 by 3 matrix. So that's 0, 3, 3. This is a 2 by 4. So this is 0, 2 by 4. This is 5 by 1. Of course, remember, this is like R5. And that zero matrix here is 0, 1, 1. So it's just notation for those matrices filled with zeros. And of course, there's a reason why we call these matrices the zero matrix or the zero matrices. It's because they act like zeros. Like for example, if A is a m by n matrix, then we have a bunch of properties that we can verify. If you add a plus 0 or 0 plus a, of course you're getting a back. If you subtract a by itself, you're going to get the zero matrix. If you have the zero matrix minus a, you're going to get minus a. If you multiply the zero matrix a by the zero matrix n by n, you're going to get the zero matrix. And if you multiply the zero matrix m by a, you're going to get the zero matrix. There's actually one property missing here that I'm going to add up. If you multiply a by the number 0, so we're really talking about scalar multiplication here, you're going to get the zero matrix. So if every entry is multiplied by 0, so that's actually a property that is missing here. So really the zero matrices, in other words, are just the higher dimensional zeros that we're used to. On the next example, I just want to go over like something very strange that we have when we look at matrices that is different from manipulating numbers. Like, for example, we have 4 matrices here, A, B, C, D, and we're asked to compute A times B and A times C, and also A times D, and then try to make some sort of conclusion of what's going on. So, for example, if we are computing A times B, so here, remember, I'll let you do the computations on your own here. Just going to maybe give you a head start with the proper structure. But when you're multiplying, when you're doing dot product between 0, 1, and 1, 3, you're getting 3, 0, 2, and 1, 3, you're getting 6. So maybe just to make you follow what I'm talking about here, let's use purple. So the dot product between 0, 1, and 1, 3, you're getting 3. The dot product between 0, 2, and 1, 3, you're getting 6. Between 1, 4, and 0, 1, you're getting 4, and between 0, 2, and 1, 4, you're getting 8. And then when you're computing AC, so you're doing the dot product between 0, 1, and 2, 3, you get 3 again. 0, 2, and 2, 3, you're getting 6. 0, 1, so second columns. 5, 4 with 0, 1, you're getting 4. And 5, 4 with 0, 2, you're getting 8. So you can see that these two matrices, that's the interesting part, is they're equal. So after you multiply A and C, A and B and A and C together, you're getting equal. So you have that AB is equal to AC, but you cannot say, hey, let's, cancel on both sides the A. So what is not true is that B is not equal to C. So there's no cancellation possible. So you cannot, you cannot cancel, like matrices. Like there's no such thing. So you cannot cancel A on both sides. So this kind of leads to the intuition that there's no division, okay, for matrices. So this is not allowed. So when you're doing this, you're doing something evil. So let's draw some of those skulls here. Okay, so it's evil. Another cool one, if you're computing AD, so starting with 2 matrices, and they're non-zero matrix. We have 0, 1, and 0, 2, and you're multiplying it with 3, 0, and 0, 7. So when you do your dot products, you're getting the 0 matrix, 0, 0, 0, 0. So that's the 0, 2 by 2. So we're using the freshly introduced notation here. And then the remark here is, well, we're getting AD equal to 0, but A is not 0. And D is also not 0. So this is like going against the factorization property, like one of the most powerful or annoying, depending on your point of view, things in mathematics. If you're trying to solve an equation using numbers, well, if you have a quadratic and you want to know when is this quadratic equal to 0, well, you're going to factor into linear terms and then just solve the linear equations in order to find those roots. Here, if you have an equation involving matrices and you want to know when is this equation equal to 0, even if you factor it as A times D, you cannot just say, well, A or D is equal to 0. Of course, if they're equal to 0, it's going to create a 0, but there could be non-zero solution to this product, and that makes life a lot harder when you think about stuff with matrices, sadly. And now, one of the last definition of this section, the identity matrices. So the identity matrices, they're basically going to play the role of being the number 1, of the matrix universe. So identity matrices, though, are not just box filled with 1s. They're actually filled with 0s. But, so first of all, identity matrices are square matrices. They are filled with 0s except along the diagonal where you have a bunch of 1s. So, for example, the identity matrix of dimension 2, the I2 matrix, is just 1, 0, 0, 1. The I3 is 1, 0, 0, 0, 1, 0, and 0, 0, 1, and etc. So the identity matrix, we use IN for the n by n identity matrix. So square matrices filled with 0s except along the diagonal where we have 1s. And they will really play the role of regular ones. Like, for example, If we look at the next example here, suppose our matrix is 1, 3, minus 5, 2, 4, and 6. Let's multiply by I2 on the left side and I3 on the right side. Why am I using different identity matrices on the left or right? Well, the reason is fairly simple. You want these products to be defined. So if you are going to multiply by 1 on the left side, because A is a 2 by 3 matrix, the only dimension, knowing that the identity matrices are square matrix, the only way this is going to work is if we have a 2 for the number of columns, and because they're squared, we need a 2 by 2 matrix. And if you want to multiply by 1, in quote, for A, so because A is a 2 by 3, and we know the identity matrices are squared, you need a 3 here in order to make it work. So the identity matrix on the right side is going to be I3. So let me just point out here, I'm just making sure you see this rule, so making sure that these things are defined. So anyways, so let's multiply I2 by A. Again here, just going to illustrate using my trick here, so the rows of the left matrices and the columns of the right matrices. So you're doing a bunch of dot products, making those columns fall. And of course, what will happen when you're going to multiply by these identity matrices, when you do all the dot products, you're just going to get, again, the exact same matrix, so nothing changes. So try, really feel it, do the dot products and see why you're getting the exact same thing again. So these matrices are really playing the roles of being ones. Not the same one on the left or right, so this is kind of strange, but this is like very typical for matrices. But when you go I2 times A or A times I3, you're getting the exact same matrices again. So in general, if you are looking at matrices of general size, so if A is a m by n matrix, if you multiply A by in, you're going to get A, just like we did A times I3 a moment ago. And if you have Im by A, you're getting A again, just like we just did I2 times A, and we got A again. So this is true in general. So these matrices are really playing the role of being the number one for real numbers, but it's not the same one on both sides, because of course matrix multiplication is not commutative. But that's it for identity matrices, but remember them, they're going to come back in the near future. Bye.